All right. Go ahead and get started. Just so we're aware, the Zoom recording is not going to work. The camera isn't working, and IT did not answer the phone. So, those of you who are joining on Zoom, sorry you don't have video feed. Not used to it. So, speaking specifically about exam-related stuff, I know we're all very interested to know about. The exam is going to be split. Once again, I'm going to mention that the exam is going to be split Tuesday and Thursday. On Tuesday, you'll be given 3 questions, and the questions are going to be mostly focused on Coulomb's law, as well as a circuits question. Just be prepared for that. On Thursday, there will be questions related to geometric optics, waves, and potentials. Potentials, of course, we covered on Tuesday. So, just helping you guys prepare a little bit there. Again, you're allowed a flashcard with any information that you want to put on there. 5x7, yes? Sure can. Any other questions? Yes.
You can bring me calculator in it. Specific calculator. Like no fancy.
As long as it doesn't have like internet access. Any other questions? Yes.
Sorry, what's the
Coulomb's law and circuits. Any other questions? Yes.
do you treat it with, I mean, when I'm going to get out or during the conference?
No, you finish the exam, you have it, then you have it. Yes.
3 questions each day.
3 questions each day, yes.
Could you repeat the
Yeah, geometric optics, so it's like reflection, refraction, speed of light, that stuff. Wave optic or waves, which is going to be, relating frequency and wavelength and speed of waves, as well as what we're covering today, which is interference. And potentials, which is what we covered last time. Any other questions? Yes.
Yes, I'm guessing not only trade. You don't have your own scan sheet, right? Or not?
Sorry, say that again?
Not your own scan sheet, right?
A scan.
Scan sheet.
Oh, scan from. No, you know scan from response. Any other questions? All right. So what we're covering today, we're going back to waves, and we're covering something that you may have seen before. We're covering interference. We're covering what happens when waves overlap. So addition of waves, when we have 2 or it works with 2 or more waves overlapping in the same region. We have 2 different behaviors that occur with interference. We can have constructive or destructive interference, and they depend on exactly how our waves are overlapping, how our waves are interacting. The interference we care about in this class is going to be due to light waves, but this applies to all types of waves. And for right now, we are going to consider having two coherent sources. Coherent sources mean that whatever is producing these waves will produce the same exact wave as one another. So let's say we have a source right here, source 1. I'm just going to put S subscript 1 for source 1. Source 1 is giving us a wave, and a wave has peaks and troughs, wavelength and frequency. We're all very familiar with this. So we draw it out. This is what wave it's emitting. Now, this can be an electromagnetic wave, this could be a wave on an ocean, this could be a sound wave. All waves behave according to this property. But what's important here is that we understand a few parts of the wave, and one part of this that is very important when we start talking about interference is wavelength. Wavelength is the distance between two parts of the wave that are the same. So we look at trough to trough, the bottommost part to the bottommost part. Wavelength is the distance between those troughs, or wavelength is the distance between these peaks. It's the same distance, it's a characteristic distance of the wave. We're familiar with this, right? Feel comfortable with this. So what happens if we have a second source? And our second source is producing a coherent wave with this first source, meaning that they will produce peaks at the same time they produce peaks, and troughs at the same time they produce troughs. So we get an identical wave acting in the same region as this initial wave. And we look and we see that with this wave, we have troughs that overlap. We have peaks that overlap. Roughly, if I drew it well, they would overlap. And what happens when these two waves add together? Well, when these two waves add together, we look at this as, a very negative value of a wave, very negative value of a wave. When you add two negatives, you get an even more negative. We have peak and a peak. These are like positive parts of the amplitude. You add these together, you get even more positive. So you add these together and you get just an even larger wave. Larger than the two individual waves. The waves add up. So our two waves add up. And under this case, where our peaks are lining up and our troughs are lining up, we call this constructive interference. So constructive interference gives us waves that add up to give us a larger wave than what we started with. If we think about two sources of electromagnetic waves, two sources of light waves, our two waves would add up to give us an even brighter light than any of the individual lights. We also have another type of interference. And our other type of interference is called destructive interference. So let's say we have source 1 and source 2. But now they're no longer producing coherent sources. They're not producing coherent waves. Instead, they're producing opposite waves. So we'll say source 1 gives us a wave, looks something like this. But source 2 gives us the exact opposite. Where source 1 has a peak, source 2 produces a trough. And so forth, right? What happens with this? Well, we look at individual spots. We look at this spot right here. We have a peak on source 2, that's a positive value. We have a trough on source 1, negative value. When we add a positive and a negative value together, we get some amount of cancellation, right? Here we have a negative for source 2. Positive for source 1. We have a bottom part for source 2 and a top part for source 1. You add these together, positive and negative give you cancellation. When you add these together, what do you get? Total cancellation for perfectly destructive interference. These are two electromagnetic waves, two light waves. You get light wave from source 1 and a light wave from source 2. You add them together, you get darkness. You get no light, no more wave. The wave cancels out. The wave is destroyed. We get destructive interference.
Did you know about the computer?
I did. The camera's not working.
Which one?
The one.
Oh, that. Okay.
No.
No.
Yeah.
And that was-
Works for every type of wave. Works for light waves. Works for waves on an ocean. Works for sound waves. Any type of wave will work like this. You may have experienced this when it comes to sound waves. You may have been in an area where there were 2 speakers and you walk around and you hear areas that are a little bit quieter. You hear areas that sound a little bit louder. These quieter areas and louder areas are areas where the sound destructively or constructively interferes. Yes.
the noise cancellation on the project.
Never going to see that.
That works a little bit differently, like noise cancellation on AirPod, well, it depends. There's 2 types of noise cancellations on headphones. There's cancellation that just comes from like sealing your ears off from the outside environment. The other type of cancellation, this active noise cancellation, which might be what AirPods do, I don't entirely know what they do. Active noise cancellation does do something like this. The AirPod will monitor what noise it hears coming in, and the speaker on the AirPod will produce the exact opposites of what is coming in. And this opposite will add up with the original sound and give you cancellation. So this is how active cancellation works, yeah. Any other questions? It's a great example. Any other questions? So now this is coherent sources. This is incoherent sources. Got it working? Got it working. Oh, awesome. Good for those of us in chat. Let me pin it in chats. Set track. Forward is what I want. No. All right. So something interesting happens when we look at coherent light and we start moving our sources around. If we have 2 sources producing coherent light in the same area, you're going to get them overlapping. But what happens if we start moving one of these sources back? Let's say we have source 1 right here. Source 2 is maybe a little bit further back. Source 2 has to travel a little bit further to catch up with source 1. So we draw source 1. It gives us coherent light, or coherent wave, because this works with all waves, not just light waves. So the first thing we see coming off of source 1 is a peak, drop, peak, drop. The coherent source 2 will do the same thing, produce a peak and a trough, and a peak and a trough, and a peak and a trough. And even though these 2 sources are producing the same exact wave, when they start to overlap in regions, we get peaks overlapping with troughs. We get troughs overlapping with peaks. What happens here? We get cancellation. We get destructive interference. Our coherent sources give us destructive interference. This peak adds with this trough, gives you no light, no sound, no wave. This trough lines up with this peak, no wave. So what brings about this behavior? The only thing we've changed is we've moved source 2 to a different location. And we've moved source 2. I'm going to use a different color for this. So it's a little bit clearer, maybe. We moved source 2. The distance back, that is that green line. We've moved it back half of a wavelength, right? So by moving our coherent sources back, by moving one of our sources back exactly half a wavelength, we get cancellation, we get destructive interference. I'm going to say that this is a delta L, change in length, or source 2 has to travel a distance delta L longer than source 1. Okay, I'll do another one over here. Try and conserve a little bit more room now, though. Source 1, source 2, we're going to pull it even further back. We're going to pull source 2 further back than we did before. Source 1 gives us our light wave. Source 2, over further down. Move source 2 a little bit further back, and after moving it just a little bit further back than we did earlier, now we're starting to get peaks lining up with peaks again, troughs lining up with troughs again. What do we get here? What happens? Constructive interference. How far back did we move this wave? How far back did we move this source? We moved this source a distance delta L equals a single wavelength, right? Go back to this picture. What happens if we move source 2 even further back? What happens if instead of moving it there, we moved it back to here? Well, get a whole extra wave. Now suddenly delta L is not half a wavelength. Now delta L is that far back. How far back is that? 1.5 wavelengths. I'm going to put 1 plus 1/2 for a reason. 1 plus 1/2 wavelength back. Here we can move this even further back. Move it back another wavelength. If we move it back another wavelength, we get constructive interference again. Anytime that delta L is equal to some integer value, and is any integer value 1, 2, 3, -1, -2, -3, 0, any value n will do this. N plus 1/2 lambda. Anytime the distance between our sources and where they end up, anytime that delta L follows this equation, an integer plus 1/2 wavelength away, we get destructive interference. Anytime we get our source delta L is equal to some integer times our wavelength. So 1 wavelength, 2 wavelength, 3 wavelength, 0 wavelength, 0 wavelength would be exactly overlapping. Anytime delta L is equal to n times lambda, we get constructive interference. Destructive interference, we have 2 light sources. Destructive interference means that if our coherent light sources are separated by n plus 1/2 wavelength, then wherever they arrive upon, you get darkness. Light plus light gives you darkness. Over here, we have our 2 light waves being created by some source. Well, if they're separated by exactly an integer multiple wavelength, then we get constructive interference. Our 2 light waves add up, give us an even brighter light. When we talk about electromagnetic waves, though, often the best way to create coherent sources of light, the best way to do that is with lasers. Lasers give us very targeted waves, right? And the problems that you're going to see today are going to be mostly the problems you're going to see in this class are going to be mostly focused on this idea of lasers traveling to a single point. So you'll see something like this. You'll have a laser here, source 1, a laser here, source 2. And these 2 lasers are going to meet. They're both going to be aimed at some singular point, right? Our lasers are very focused. They give us a single location. So get 1 wave from source 1, 1 wave from source 2. They add up. Do they constructively interfere? Do they destructively interfere? Well, it depends on how far each of them had to travel. Source 2 had to travel a little bit further, right? How much further did source 2 travel? Well, we got a nice right triangle there. If we know a couple of the lives, we can figure out total distances traveled. Figure out what the difference in length is here, right? Gonna have just that slight extra bit of travel. And that slight extra bit of travel, that is your delta L. Does that make sense? Do we see how source 2 has to travel just a little bit further to get to our ending location? Now, there are very, very easy ways for us to create this situation. And creating this situation gets into physics experiments called double slit interference, double slit diffraction. And we'll play a lot with that as we move forward. For right now, just know that if we create two sources, we can tell, do they constructively interfere? They constructively interfere, they give us a bright light. They destructively interfere, they give us no light at all. We'll play around with this more in future lectures. We'll play around with this a little bit more when it comes to lab. But for right now, we just want to work on this map, understanding this idea that changing distances is what will cause constructive or destructive interference. Are there any questions, thoughts, comments, ideas? Feel okay about this?
Sure.
Sure. Did we see interference in 2500? Yes? Kind of? Maybe? No? All right, well. Let me go ahead. Slide video unmute perhaps. The problems we're going to be working on right now in regards to interference are not overly complex, not overly difficult. But I do want you to think specifically about the concept that's going on here. When you're solving these interference problems, I want you to understand that this delta L right here is what really matters, and you will usually solve for that delta L using geometric properties. Yes. Sure is. September 15th, that's the day, right? Yeah. Looked at the clock to see what day it is. It's going to work out. All right. So work on this. Ask if you have any questions. Your LAs and I will be walking around helping out. There's questions in there about reflection and refraction. Be sure that you understand what those questions are asking. And I think there's also potential problems. Be sure to ask if you need any help. Got it? All right. Let's go ahead and get started. So your index of is fine. Index of speed of light is speed of light. So 1.3 is speed of light in this water. Were you able to find distance? No.
You know this. So we have this angle from Yeah, so the way I ran the problem, this one is. That this is. And if they found so solve this and figure out. If they take alpha divided by lambda. You just relate these. Distance. Yeah. Oh. So.
That gets back to just this idea of that.
So you just look at it. So it's a question for. You small bit easy. Right. Okay. Yeah. Very good. Thank you. Yeah. Oh.
Maybe you're right.
Yeah.
Oh, actually.
Yeah, one and a half.
So like, let's say like this is too bad.
No, sorry, or legislative.
And that makes sense, right? Because
Well, that means that there's just.
So you end up with.
Yeah, yeah. First is that.
So how does that relate to the wave? What do you think?
What's the final county of what you just said?
So it's. Yeah. So, or delta L, would be one times our wave. It's weird, and when you look at these things for light wave efficiently, you're always going to have a very small amount because light waves are wavelengths. Very small. So you're gonna solve the delta, right? The delta is gonna be a very time. If you solve for it, you're gonna end up finding that delta L is gonna end up being 5%. Exactly what it is. So delta L is equal to 1 times. That makes sense. So if it had to come up to be like 1.5 times our wavelength, then we get these stuff. But because it's an integer multiple of the wavelength, we get construct. Does that make sense? So, what you should look for is solving for n, right? So, if you solve for n, then you find that n is equal to 1. Well, then what you have is constructive. If you solve for n, and you find out that n is equal to 1, then it's going to go something. 2, 3. What you're going to do is you're going to take see what that is. We give you 1, 2, 3. If it's an integer, any integer, so 1, 2, 3, -2, -5,000, you get constructive. If you get an integer plus 1/2, then you get these. Because just the number of. Does that make sense? It all comes out of figuring out these deltas.
So I don't know. It's not how you, so you can just plug it in, so like, I know you hear. That, like, my house is mine, I'm guessing you wouldn't have the value from that.
We are looking, we're going to see, this is solve the equations.
Yeah.
Yes.
Well, what we're finding with the estimation is. Yes. So, I mean, finding out is a goal.
Yeah.
So,
So what we're gonna do is think about what if we solve them? What if we do delta L for here? Let me. We do delta L for here. So we're gonna take. We're gonna see how does delta L. If we take this relationship, we end up with integer plus all of that in these. You just get another one. I'm gonna say. One meter. The second source probably. Right. We know that millimeter. Yeah. So we want to find out how far does this one. Yeah. If you find L2, then graph out past L1. Yeah. I do. Much further. This kind of it's up to you. Let's you're gonna end up with a very small. I don't think mine is like.
You made it by. You got a line.
You're on his name.
You got a line. Yeah. Yeah. So.
little given. Also, what's the wavelength of the so 5. Then onto the record. Is length, which in our case was 5,
No, I did it. I was just telling you.
is equal to any coefficient at the we have it 5, 8, 7 here on the left side. Right side.
Well, sound down.
Kind of like find the way that. But on the right side.
So this is the side is the same.
But we're getting away from this, so that you can see. One for constructive, one for constructive.
Right?
But you don't want to think about it. Oh, it's not. So we want to deal with this.
Yeah. It's a bit long.
Close to, yeah. But we're not, at least. And you multiply that. But they didn't ask for constructive. Well,
Yeah.
Or delta L. Given delta L, it's all.
Yeah.
I got 4.
Yeah, I already heard that.
I got a million.
Question. Pause.
Yeah.
So. So, we have our total line policy. So this one has a problem out here. This one has a problem one more.
So that's. They could just.
So what you'll find.
I know.
So if you take delta L, divide by half, we get a whole number, 1, 2, 3, 4. If we get then we fit. No, it's just one of them.
Yeah, or. Yeah, so they put it on there. Yeah, so you want to right? So you.
So that's, then I try and work together with that.
So here.
But now that I see it, that's just the difference.
So this is what your, allocated.
Or plus in line, two plus that. Get plus that, so you get the high five, so you can take care of what you put it on. Let's go.
Right, yeah.
And then once you do that. That's where.
I'm having trouble finding the shape.
Now. That's really cool. Oh, you get. You know that, no, I'm looking at the difference.
Yeah.
I talked to. Oh, yeah, yeah, but. Stuff that now is. For our. Then you have two elements. Then you have two rating on a test.
Oh, yeah. I haven't really installed it.
Delta L is the. It's not correct. Oh, I know that. Then you have to input it. Let me give you a random one. Let me give you a random value. Yeah, there you go. Random value. Those are three. We have two. Yes. And you know that. Oh, yeah. Really? I'd say that. What's the value that I like? Geez, really? Oh, did you use this one? I know. Oh, it's from last time? So we don't know what. I don't think we know. And it could follow. We don't know. What is this called? All right, here's one side. You know that when this is the difference between we're just like this line. One thing I have to do is now. You know the these problems
Yeah.
we have this line. Those are all the this line is 2. We said 2.
So we heard on the
We're already have our things. We already have our gains. So we have stage where we have this. Oh, they're just. Yeah, just put that out. This number. Oh, I know. Oh, yeah. Yes. Oh, yeah. And so I Yeah, very, basic time things. So,
That's the thing, we want this set up here, so it's delta L equal to N plus 1/2.
Yeah.
I know that would give that would be for error.
Not sure how that worked at all.
What's the untitled error?
let's see.
You have that, that's your. And we struck that.
Where the, use that. I thought it was, yeah, I thought it was.
This tells us what it is. See, that's gonna be a hypothesis. In this case, two times. And then delta.
So for,
The difference.
I think we even.
You next to trying to.
Oh, since.
This can have. We have lambda, we know what.
So.
We wanted to go out. This one.
And so, because it's zero, this is placed to be half.
Yeah.
I got and then what I did was I just added this L here, and that'd be the minimum.
And then you know that
And then. Yeah, but you kind of. Like. Did that, and additionally, they just saw it.
No.
Yeah.
So.
Oh, yeah.
Yeah.
Because your eyebrows are.
Then you're right, yeah, 9.5. So I can remember that, but yeah. Assuming that's right.
But we know that. See, this is.
So we usually, they give us the. So we just try to solve those.
So that, okay, better?
Yeah.
I think I might have to get to work. But yeah, you get the thing. My brain is not.
So I found the
Oh,
angles.
I'm gonna do it.
I don't know how to use the.
I was thinking of, there was only like 30 questions. But I used them the whole- The way you like, it's like, you know, most of the games just have to do like a normalization. Yeah. But it's okay, you actually have to like think about it. It's not the easy.
Yeah. Oh, my bad. Oh, okay.
Yeah.
I think that was the final.
I know this one.
Got it.
Okay. Oh. All right.
Oh, yeah. What is that?
But I was like, oh.
Yeah.